Let few more students join, then I will start. Everyone, reinforced beam. Design of doubly reinforced beam using limit state method. Last class I have discussed about lintel beam, the design of lintel beam. I hope all of you have understood it. Let me share the screen. So let me start today's class. Today I will discuss about the design of doubly reinforced beam. Till now we have discussed the design of singly reinforced beam. We have seen various practical examples of a singly reinforced beam, that is in terms of cantilever beam or lintel. So in major practical purpose, we have beams for your day-to-day construction. If you see any building for any major work, the beam mostly preferred is doubly reinforced beam. Just a minute. I'm having some problem with presentation. अच्छा, उसके को- It's about the difference between singly reinforced beam and doubly reinforced beam. So in singly reinforced beam, till now we have dealt with the reinforcement that is applied only on the tension zone. Okay, means for a simply supported beam that is below the neutral axis. So we can say the singly reinforced beams are those beams where the reinforcement is provided on the tension zone only, and no reinforcement is provided to carry the compressive force on the compression zone. Okay, but we will have a hanger bar in the compression zone to hold the shear reinforcement, the stirrups, but that should not be considered as compression zone reinforcement. So this is the definition of singly reinforced beam, which is provided on the tension zone only. In case of doubly reinforced beam, as you can see in the diagram, that both the compression zone and the tension zone, the reinforcement is provided. From reinforcement, we means the main bar, the main vertical bars which are running through the span of the beam. Okay, the vertical, the horizontal main bar. So, this discusses about the design of this doubly reinforced beam, and now the reason comes why are we dealing with the doubly reinforced beam? Why reinforcement is to be provided both the tension and compression zone? Why it is necessary? Because we know that our concrete is well conservant in taking part is taken by the reinforcement, steel reinforcement, the tension, but concrete is capable of taking compression. So why the doubly the compression zone also? Okay, this is the question that may arise. So the answer is real purpose. We have to make sure that the size, the depth of the beam should be restricted. Okay, we make sure that the depth of the beam is restricted to certain height, to a maximum height, suppose for architectural purpose. For in general condition, I'm saying. So when we are actually we are trying to reduce the depth of the beam, we are actually compromising the movement resistance, the resistance of the movement that is to be carried by the beam, and that depends on the depth of the beam. So what we see that if not enough moment of resistance is sufficient uh, to resist this bending moment, then our design won't be fulfilled. If we increase the reinforcement, okay, to the external bending moment, that is actually restricted because that will render our structure, our beam as over reinforced, and this over reinforced structure beam is not acceptable, we know, because of economy purpose. So we have basically two options in hand. moment of resistance of beam without. Okay, so we have actually two options in hand to increase the moment of resistance. First option is we can increase the. Okay, so that is not possible. Another way is so our beam has also an option is okay. So by introducing this concept of reinforcement, we can actually increase our resistance without, and this is how we can fulfill the purpose. Our session began. All the conditions are fulfilled. So this is basically you can say for doubly reinforced beam is utilized for practical for all major work to be done with the beam. Now the reinforcements, now for a single reinforcement, if you provide reinforcement in compression zone, that is actually that is we providing for the hanger bar, like for providing support to the stirrup. Okay, so that should not be confused with the compression zone reinforcement. Okay, so from here we can conclude that to increase our moment of resistance of the section of the beam, we can actually apply doubly beam. Okay, to fulfill all the and without compromising its economy or the threat to the beam which will be having for a one reinforced section is the sudden failure of the structure, actually over reinforcing that will fail suddenly without any warning. So that could be also, that problem could also be taken care of. Okay, so beside this purpose, uh, we have other purpose also, the reason for which doubly reinforced beams are considered. Okay, so some of the points are described here. So we know that if we all the forces that are coming on a structure, but means we know that there is dead load, there is live load, okay, self weight of the structure. So all these forces are vertical in nature. Okay, but beside this, there are also horizontal loads in the form of earthquake, in the form of wind load, okay, which are coming to the structure. So due to this, you may sometimes also find that there is a change in bending moment of the beam when the load is considered in the lateral direction. Means both the positive bending moment and negative bending moment can be seen on a span of beam. Okay, so this external load that is in the terms of your lateral load is to be counted. Then for those we have to also consider reinforcement at the compression zone. Okay, another point could be due to eccentricity of the load. Means the load may not be applied at the midspan or to the neutral axis. It may be eccentric, it may be falling outer to the structure. Okay, and because of that there will be formation of bending negative bending moment at some portions of the beam. So that has to be countered. So that is why this compression zone reinforcement is necessary. Okay, there may be loads like your accidental lateral thrust load, okay, shock or impact load due to your, it could be due to your some blasting or due to earthquake forces which are lateral in direction, or due to some failure of the structure, some nearby structure which has failed and fall down onto a well conditioned structure, and that lateral load is to be sustained by the beam. So for that, there will be generation of sides negative also generate, and for that we have to provide reinforcement at both the ends, at tension zone also, at compression zone also. Okay. Another requirement could be to fulfill your ductility. So this ductility could also be fulfilled by providing compression reinforcement. Okay, we can reduce the long-term deflection by providing compression reinforcement. Right. So these are the major points which are actually and the purpose for which doubly reinforced beams are used over your singly reinforced beam. Okay, but this compression zone reinforcement should not be confused with the longitudinal hanger bars. Okay, that is applied in the compression zone for your stirrups, for holding your stirrups, or anchor bars that we have discussed in previous class. ठीक है, सबको समझ में आया अभी तक जो डिस्कस हुआ? All of you understood what are the advantages of doubly reinforced beam over your singly reinforced beam, why it is applied, why it is necessary? Or should I repeat some point if you want to discuss? Am I audible?
Yes, sir.
What's the problem? Thank you. And so the reinforcement will be dealing with the equations. So figure you can see there are figures shown. Section 1 is the section for your singly reinforced beam, where the reinforcement area AS is applied, is available there at the tension zone, that is singly reinforced beam. So actually doubly reinforced beam is what? It is the combination of this singly reinforced beam compression zone also, that is ASC, area of steel in compression zone, ASC. So it is the combination of this that comprises two. There is also tension reinforcement, extra tension reinforcement is also available. Okay, at the tension zone AST2. So this is the extra tensile with the compression zone reinforcement. The summation of all this reinforcement will actually form the whole section of the doubly reinforced beam. Okay, so this doubly reinforced beam could be seen the summation of two different sections of structure. Now if you see section 1, the moment of resistance till now we have seen that it is mu limit. So this mu limit is dependent, that is the tensile steel. Okay, now you see section 2. In section 2 we say the moment of resistance as mu. This mu2 will be comprising of the steel that is available at the compression zone, that is AC, and additional tensile steel, that is AST2. Okay, that is required corresponding to AC. So mu is actually summation of mu limit plus mu2. Okay. Now you see the section diagram. The effective depth is small d. We know there is d dash compression zone enforcement. D dash is your what? Who can tell? D dash kya hai? Can anyone guess? Not guess. Can anyone tell from the diagram? You know, I have already discussed what is D dash. You know the term D dash kya hai? Can anyone try?
Sir, effective cover.
What is D dash in the compression zone? अगर ये टेंशन जोन के लिए होता means what you can see from the figure, the distance of centroid पकड़ लो, centroid of the reinforcement outer nominal cover, what is that distance called? Anyone? The clear cover. Yes, Buddhadev, you are not audible. Sir, which is clear cover? You are not audible, Buddhadev. You are unmuting, but sir, clear cover. Okay, it is your effective cover. All of you know what is clear cover and what is effective cover. I have already discussed. If you have forgotten, then you refer to previous notes, previous slides. Okay, the difference, the what is clear cover, what is effective cover, what is effective span, all of you must know. Okay. Okay, I'm moving to the next slide. So the width is B and effective depth is small d, and this d dash is your effective cover in your zone. Now let us discuss the stress diagram of your doubly reinforced beam. Okay, so this diagram is familiar to you. Okay, you have already seen the stress diagram for limit state for a singly reinforced beam. It is similar to that. The tension, the strain diagram is similar. The values you can see is similar. Okay, for your compression zone, the strain diagram, the strain value is 0.0035. See is the distance of this strain at your where your compression zone due to concrete is falling. Okay, so that is actually C2 in your stress diagram, as you can see, and the at your the strain diagram you can see it is the triangle, the base of the triangle value is 0.87 fy by es plus 0.002. Okay, we have already discussed this. Okay, so while drawing the strain diagram, stress strain diagram, be careful that whenever you are drawing, make sure that the uh, at the bottom the stress value, the strain and stress value, where it is, you have to draw up to the reinforcement only. You have to draw for effective depth, okay, not for your overall depth. Sometimes students make mistake, they uh, consider the overall depth, so that should not be taken. See the stress diagram, strain and stress diagram, the this value of maximum strain at compression is lying along with your tension zone steel, okay, means at the depth of your effective depth of the beam, not the overall depth. And also the compressions for your compression zone, the stress diagram, the value of overall tension is 0.87 fyast, okay. Compression C1 and C2, we will just see what is C1 C2 next on the next slide. These are the two compression. These are the two compressions that C1 and C2. C1 is actually for the compression due to due to your whole concrete structure in your compression zone, because the concrete will be taking the compression C1, and with addition there will be C2, that is your compression reinforcement, compression zone reinforcement. So two compressions are actually acting, C1 and C2. Um, and these are the corresponding so see the depth of C1, that is acting at 0.42 XU. Okay, we know that the maximum compression is 0.446 FCK. So at a distance 0.42 XU, this C1 is acting, and C2 is acting at this compression reinforcement, that is the effective depth, effective distance of the compression reinforcement from the extreme fiber, extreme concrete fiber, that is D dash. FSC is what? FSC is the stress in compression steel. Okay. ASC is what? ASC is the area of compression steel, and FCC is your stress in concrete at the level of steel. So these are the extra terms that have been included with your singly reinforced beam compared to a singly reinforced beam. These are the extra terms, and remaining things are same. Okay, I hope it is clear. Now moving to the next slide. Uh, all of you first draw this stress diagram. Okay, all of you just draw this stress diagram in a piece of paper. It will be easy to explain the values, how it is coming, C1 and C2. Uh, you. Okay, so all of you just quickly draw this stress diagram. Uh, it is a simple diagram, and you know it is up to a distance it is straight, then it will be parabolic. When you are running your stress diagram from top extreme fiber of concrete up to neutral axis, the value of, see the tension value T will be comprising of two tensions, that is T1 and T2. T1 is the tension that is for your singly reinforced beam, that will be available, okay, that is 0.87 FIST1. And additional, there will be additional tensile reinforcement due to the corresponding compressive reinforcement, that is AST2. So our tension becomes T2, that is 0.87 FY AST2. Okay, so T is equal to T1 plus T2, and corresponding value of uh, compression for this compression zone, value of C1 compressive stress. This compressive stress is for your reinforcement that is at a distance of 0.42 XU. So the remaining distance below C1 is equal to D minus 0.42 XU. And this value of C1 is actually 0.36 FCK BXU. Okay, this is the corresponding value of stress at the distance 0.42 XU. And the maximum value of this stress at the top we know is 0.446 FCK. And the value of C2 will be for corresponding tensile reinforcement, and the distance is the effective compressive zone distance, effective so that is D dash, and the distance from bottom means the lever arm distance is actually for C2 and T2 is D minus D dash. Okay. Now let us see. Now to calculate this value of XU, you need the value of C1 and C2, and we know that C1 and C2 are the total compression, and where C1 is the force that is carried by the concrete area, and C2 is the compressive force carried by the compression steel, means ASC. ASC is the total compressive steel that is applied. So value of C1 is 0.36 FCK into B into XU. B is the width and XU is the depth of neutral axis that we have to find. C2 is FSC into ASC minus FCC into ASC. Okay. FSC क्या है? It is the stress in compression steel, and FCC is the stress in concrete at the level of steel. Okay. एक है तुम्हारा compression steel, उसके लिए ASC होगा, और एक है concrete at the level of steel. So of the compression steel, FC, and also the stress of the concrete at this level of compression zone steel, that is FCC. So actually this C2 stress in steel in compression zone, and it is not including the value of stress in concrete at the level of steel, so we have to subtract it to S. Okay. Now since this portion of the concrete where there is steel is embedded, so there will be no concrete, so that is why this value is to be subtracted. So total compression will be summation of this values C1 and C2, and we also know the total tension is 0.2 C2, that is equal to T. We will get the corresponding value of XU, and value of C is very small. Okay, the value of stress in steel at the value of stress in concrete at the level of steel is very small compared to the value of stress in steel Okay, because only a negligible quantity of steel is there at that portion, and that portion could be avoided for the compressive stress that is coming for concrete. So, ignoring that, neglecting that, the value of FSU is equal to stands as 0.85 by AC minus FSC into AC FSC. So we get the depth of neutral axis from here. Okay, I hope all of you have understood. So from the stress diagram, we will get the corresponding value of mu limit for the balance section. We will get the corresponding moment as mu limit, and the moment of resistance for additional section of AST and ASC we will get in terms of mu2. Okay, I hope this all of you have understood this. No problem. Next, let us move to the calculation of moment of resistance. So we know that moment of resistance is equal to the value of corresponding compressive force multiplied by the lever arm distance stands as C1 into lever arm. So value of C1 you provide, and mu2 is your C2 into lever arm. So value of lever arm for C2 is d minus d dash, and value for lever arm for C1 is u. Okay, no problem. Now the value this for mu2, this additional value FCC into ASC, for this loss in concrete we have to also include, and ultimately the value, the total loss of concrete by neglecting it, the value of mu turned as 0.36 FCK into B into XU multiplied by D minus 0.42 XU plus FSC into AC multiplied by D minus D dash. Okay, I hope no problem for understanding this equation, how it is derived, how it is formed. You just read for your balance section means for mu limit and mu2. From here we will actually get the value of FSC. This is actually the stress in compression steel, and this is obtained from the equilateral triangle. Okay, similar triangles from the strain diagram. So if you see the strain diagram for corresponding compression zone steel is epsilon SC. So to find this value of epsilon SC, we have to see the strain diagram, and from equilateral, from similar triangles, we can say that 0.0035, which is the extreme, which is the maximum strain at compression zone, divided by XU, which is the neutral axis distance, is equal to epsilon SC, which is the strain at the compression zone for area of steel ASC, divided by the distance, that is XU minus D dash. Okay, overall depth is XU, means up to the neutral axis, and subtracting the effective cover D dash for the compression zone. So from here we will get the value of corresponding value of epsilon SC, that is 0.0035 into 1 minus D dash by XU. Okay, all of you understood, I hope. No, just refer to the this strain diagram figure. Strain diagram figure. We will get this value of epsilon. Now next, for this corresponding value of epsilon SC, we have to find the stress at the compression steel, means FSC. Okay, and that actually is obtained by 2A. One, you can use IS 456, where the string, the value of stress is given for corresponding steel. Okay, the and with the corresponding value of strain, the stress is obtained for value of, for a particular value of Fy, grade of steel 500 or Fe415, or else you can check SP16, that is the design aid. So to obtain this corresponding value of Fy, we have to actually use this in SP16 design aid, that is table F, where from where you will get the value of D dash by D for corresponding value of grade of steel. So this is actually what? This is actually your value 0.87 Fy. Okay. For this corresponding value of 0.05, you see it is 0.87 Fy, that is 217. 0.87 into 250, that is 217. So for all this value of D dash by D, it is equal to or above 0.05, the value of your stress in compressive steel. And to find the intermediate value, we can interpolate. Okay. Let us discuss the procedure, how to find the moment of resistance if a section is provided. So these are the steps that we have to follow. So if suppose a dimension of beam, if given is B in B by D, okay, and you are provided with the area of compression steel and area of tensile steel, and also the grade of concrete is given, and considering cover of compression steel, that is D dash. So first we have to find the value of d dash by d ratio. Okay, for determining the value of FSC from the table 1 that just now I have shown you. Okay, so after that we have to determine the value of neutral axis. So by from the value of FSC, the obtained FSC from the table from by using SP16, we okay. FSC is what? FSC is the stress in compression steel. Next is to we have to determine the value of XU max. Okay, that is by comparing the values that are obtained of XU and XU max. Next is to the value was so using this value and neglecting the value of FCC, mu, and value of the you have to again the calculator and the how we have to do the design. That's all for today. All of you write your name and roll number for today's attendance. If you have any doubt, you can say, you can ask. You can solve simple problem for this. Okay, I'm giving you a problem. All of you try to solve and show me later on. I'm writing a question in the chat box. All of you follow it and write it down, and later on you can solve it. Okay, I have given a problem. Or if you just check your chat box. Okay, determine the factored moment of resistance of a beam 250 mm by 350 mm. 350 is the effective depth. The beam is reinforced with two numbers 18 mm dia bar, numbers 20 mm dia on tension. Okay, read it as dia. It did by autocorrection on tension zone. So find the compression bar. So the compression bar are placed at a distance of 40 mm from the top and use M20 Fe415 steel. So all of you try to solve this problem. You have to find the factored moment of resistance mu, and for the corresponding value as shown in the table, you have to find the value of FSC from d dash by d ratio and find the neutral axis depth. Then after uh, you will check for XU max. XU max for Fe415 is 0.48d. So check whether it is coming within limits, and if so, then just calculate the factored moment mu. You can do it now if you want. Try to solve it. See if you can do it. I can provide you the ratio of d dash by d. Okay, that is your 0. That is your 0.1. The value, and from there the value of FSC is 535 Newton per mm square. Okay, so next you can just apply the depth of neutral axis formula, and these values are coming or not.